There are new, strange discoveries about 3I Atlas, and scientists are honestly baffled. A mysterious visitor from another star system has entered our solar system, and it's defying every rule in the cosmic playbook. 3I Atlas isn't behaving like any comet we've ever seen. Instead of lying dormant in the freezing dark, it's glowing, venting gas, and shifting shape in ways scientists can't explain. Telescopes around the world are capturing data that challenge everything we know about how matter and chemistry work in space. As the eerie green comet drifts through the void, one haunting question lingers. What if this isn't just a comet, but a clue that our universe itself might be something far stranger than we imagine? So, if you want to know everything about the strange recent discoveries about 3I Atlas then, watch this video till the end and subscribe to the channel. Let's begin. Far beyond the orbit of Jupiter, where sunlight is weak and space grows bitterly cold, something impossible is happening. 3I Atlas, this mysterious interstellar wanderer, has begun to stir to life. Astronomers watching through the world's most powerful telescopes expected it to remain a frozen, silent body until it came much closer to the Sun. Yet, to their astonishment, it's already active. Plumes of gas have been seen jetting from its surface, and a faint, glowing coma, that hazy shell of dust and vapor, now surrounds it, shimmering eerily in the darkness where no comet should glow. At that incredible distance, temperatures plunge to more than -200 degrees Celsius, cold enough to keep most known ices solid and inert. Under normal conditions, a comet wouldn't even begin to melt or show activity until it crossed the orbit of Mars, maybe even Earth. But 3I Atlas defied those expectations completely. Instruments detected streams of gas escaping from its nucleus long before sunlight could possibly heat its surface. It's as though something deep inside this object is breaking every rule we understand about thermal physics. This early awakening suggests that 3I Atlas contains ingredients far more volatile than the frozen water or dust that make up ordinary comets. Something within it is reacting, vaporizing, and creating energy at astonishingly low temperatures. But what exactly? That question has set off a chain of scientific debates and sleepless nights for researchers worldwide. Observatories across Earth and space, from Hubble to JWST, have turned their eyes toward this glowing phantom, hoping to understand how it can come alive so far from the sun's warmth. And as they peer deeper, what they're finding is even stranger. The gases bursting from 3I Atlas hint at super volatile compounds, exotic ices that evaporate almost instantly, even in the coldest parts of space. These rare substances could be the key to its mysterious behavior and to understanding where this cosmic visitor truly came from. The strange early awakening of 3I Atlas has forced astronomers to confront an unsettling truth. The only way a comet can show such intense activity so far from the Sun is if it's made of super volatile materials, substances so delicate, so easily vaporized, that even the faintest glimmer of distant sunlight can make them erupt into space. Unlike the familiar comets of our solar system, which are mostly made of water ice, dust, and rock, 3I Atlas seems to contain carbon dioxide, CO2, and carbon monoxide, CO, in abundance, both of which sublimate or turn directly from solid to gas at temperatures far lower than water ever could. To grasp how bizarre this is, imagine standing somewhere near Jupiter's orbit. The Sun is just a bright star in the distance, its warmth barely perceptible. At those freezing depths, water ice is as solid as granite. Nothing should melt, nothing should move. Yet 3I Atlas is erupting, glowing, and venting gas as if it were bathing in summer heat. This means that within its frozen body lie vast reserves of carbon-based ices that can evaporate at just a few dozen degrees above absolute zero. In other words, this comet carries material so fragile that it behaves as though space itself is too warm for it. Astronomers call such substances supervolatiles because they are extraordinarily sensitive to even tiny changes in energy. On Earth, carbon monoxide and carbon dioxide exist naturally as gases. But out in interstellar space, where temperatures dip below -250 degrees Celsius, they can freeze into solid ice. These ices are thought to form only under extremely cold and stable conditions, far colder than the regions where our solar system's comets were born. The fact that 3I Atlas is dominated by these supervolatiles hints that it was forged in a very different environment, perhaps on the outermost edge of an alien solar system, or in a molecular cloud so cold and dark that sunlight never reached it. This makes 3I Atlas more than just a comet. It's a time capsule from another world. Every molecule within it tells a story of chemistry that unfolded light years away, possibly before our own sun even ignited. And when those molecules escape into the vacuum of space, they bring that alien story with them. As the gases vent and the coma expands, scientists are effectively reading the comet's biography in real time, analyzing the light it reflects and emits to decode what it's made of and where it may have come from. The first spectroscopic readings from Earth-based telescopes shocked even seasoned researchers. Instead of the typical mix of water vapor, carbon dioxide, and dust seen in most comets, 3I Atlas displayed an overwhelming dominance of CO2 and CO-, so much, in fact, that it appeared to have more carbon dioxide than water. That's unheard of in any comet observed to date. In our solar system, water is always the most abundant ice, with CO2 and CO appearing only in smaller amounts. But in 3I Atlas, the balance is flipped, almost inverted. This inversion tells us that 3I Atlas couldn't have formed in an environment anything like our early solar system. In the region where our comets formed, temperatures were cold, but not cold enough for carbon monoxide to freeze in large quantities. For CO to condense and remain stable, it must form in places so frigid that even the cosmic microwave background radiation barely warms the dust grains. That means 3I Atlas likely originated far beyond the snow line of its home system, perhaps in a zone so remote that its star was little more than a distant point of light, a faint reminder of heat it would never feel. This realization is staggering because it implies something about the diversity of planetary systems across the galaxy. If comets like 3I Atlas can form in such distant, frozen realms, then other star systems must host environments far more varied than our own. It means that the ingredients of life, or at least the chemistry that leads to it, might be scattered across far stranger and colder regions than scientists once thought possible. But it's not just about where 3I Atlas came from. It's about what it's made of right now. These supervolatiles don't just tell us about its birthplace, they shape everything about its behavior. The jets of gas that stream from its surface act like tiny thrusters, subtly altering its motion as it speeds through space. Astronomers have already noted that its trajectory seems unusually stable, as though its outgassing is somehow balanced or controlled. Another curious trait that sets it apart from typical comets, which often tumble unpredictably when venting gas. There's also the question of how these supervolatiles have survived. Over millions or even billions of years traveling between stars, most comets would lose their most delicate compounds to the radiation and cosmic rays of interstellar space. The fact that 3I Atlas still retains such volatile material suggests that it has been extraordinarily well preserved, perhaps protected deep beneath an insulating crust, or locked away within a structure denser than expected. Some theorists have proposed that it might even be encased in a layer of organic material, a kind of natural shield formed from carbon-rich dust, that has kept its inner ices intact since the dawn of its birth system. When those gases finally erupt into space, They don't just form the comet's glowing halo, they create an entire ecosystem of chemistry. Molecules collide, break apart, and reform under the radiation of the distant sun, producing strange compounds that shine in ultraviolet and infrared wavelengths. In this way, 3I Atlas becomes a floating laboratory, a rare window into reactions that no Earth-based lab could ever reproduce. Scientists are now cataloguing the comet's emission lines in painstaking detail, trying to trace how its chemistry evolves as it moves closer to the sun. Early results show that the gas composition isn't static. The ratios of carbon monoxide, carbon dioxide, and other compounds change over time, suggesting layers within the comet's core are being exposed and exhausted at different rates. This dynamic activity indicates that 3I Atlas isn't just evaporating randomly. It's a complex, evolving system with internal structures that control how it vents material into space. To put it simply, 3I Atlas is alive in a chemical sense. Its reactions are constant, unpredictable, and beautiful. A cosmic dance between light, temperature, and time. Every jet of gas, every pulse of its coma, whispers secrets about its alien origins. And as strange as this super volatile behavior is, it's only the beginning. Because the more scientists observe, the more they realize that 3I Atlas isn't just active, it's explosively active. NASA's instruments have recorded staggering amounts of material being ejected every second, as though the comet is venting its lifeblood into space in one grand, chaotic performance. This leads to the next mystery, one so intense that it's being compared to a celestial fire hose unleashed in the void. When NASA turned its instruments toward 3I Atlas, what they saw made even the most seasoned comet researchers stop and stare in disbelief. This interstellar traveler wasn't just active, it was furiously alive. In a report that quickly rippled through the scientific community, NASA described the comet's behavior as venting water vapor like a fire hose, a phrase that perfectly captured the sheer violence of what was unfolding hundreds of millions of kilometers away. Jets of vapor and ice particles were blasting out from its surface at breathtaking speeds, throwing tons of material into space every single second. At first, no one believed the numbers. Could something so far from the sun, where light is barely more than a distant glimmer, really be shedding that much water? But repeated observations confirmed it. Instruments aboard multiple observatories, from the Hubble Space Telescope to NASA's NEOWISE and infrared ground-based arrays, all picked up the same unmistakable signal. Enormous quantities of water vapor streaming off 3I Atlas, creating a massive cloud that stretched thousands of kilometers around the nucleus. In essence, the comet had become a self-made fountain in the void, spraying its essence into the emptiness of space. The physics behind this phenomenon left scientists both awed and confused. Normally, comets begin venting water vapor only when they reach the inner solar system, typically near Mars's orbit or closer, where solar energy is strong enough to sublimate turn directly from ice into gas, the frozen water locked within them. But 3I Atlas was already venting with volcanic intensity while still orbiting far beyond Jupiter, where temperatures hover around -230 degrees Celsius. At that temperature, even supervolatile compounds struggle to escape into space. So how could water, which requires far more heat to vaporize, be erupting so violently here? One leading theory is that 3I Atlas's surface may be riddled with deep fractures and porous vents that allow trapped gas from within the nucleus to burst outward. Over billions of years in the icy blackness between stars, cosmic rays could have fractured the comet's crust into a network of channels. As the faint warmth of the distant sun penetrated its surface, volatile gases like carbon monoxide or methane might have started expanding within those cracks. This slow internal buildup of pressure could have forced pockets of water ice closer to the surface to erupt explosively, not because the sun melted them directly, but because the comet itself became unstable from within. Another possibility, even stranger, is that 3I Atlas's composition includes amorphous ice, a highly porous form of frozen water that can trap gases in its structure. When this kind of ice warms slightly, it can suddenly collapse, releasing both the trapped gases and the water simultaneously in violent bursts. Laboratory simulations show that this process can produce jets powerful enough to fling dust, rock, and gas far into space, exactly what we're seeing now. If 3I Atlas is rich in this amorphous ice, it could explain the fire hose effect NASA observed. The implications are staggering. The comet may be losing so much material that its mass and shape could change dramatically during its journey through our solar system. Estimates suggest that every second, hundreds of kilograms, perhaps even tons of ice and dust are being expelled, forming a thick, turbulent coma that reflects sunlight in dazzling patterns. This massive loss means that by the time 3I Atlas leaves our cosmic neighborhood, it could look completely different. A ghost of its former self, stripped of its outer layers, perhaps even fragmented into multiple pieces. Astronomers have watched similar events before. Comets like Ison and Atlas, no relation to 3I Atlas, disintegrated when their internal pressures grew too high. But this case is unique because 3I Atlas isn't being torn apart by heat from the sun. It's being devoured from the inside out, as if something ancient within it has finally begun to stir after eons of cosmic silence. Some scientists have even speculated that this internal volatility could be due to a chemical imbalance. Perhaps the comet contains unknown compounds that react with sunlight or cosmic radiation in unpredictable ways. The fire hose analogy is more than poetic, it's literal in scale. At full force, the jets on 3I Atlas could expel more than 10,000 liters of water per second, enough to fill an Olympic swimming pool in under 2 minutes. The vaporized ice quickly freezes again as it rushes into space, forming sparkling plumes of frost that scatter sunlight, giving the comet its shimmering, halo-like appearance. Each burst reshapes the coma, creating visible ripples that scientists can actually watch evolve in real time through powerful telescopes. This violent venting also affects the comet's motion. As gas and dust are ejected, they act like miniature rocket thrusters, subtly altering its trajectory. These non-gravitational forces are measurable, and astronomers tracking 3I Atlas have noticed small deviations in its predicted path. It's a delicate reminder that this object, though vast, is governed by the same laws of motion that send spacecraft across the stars, and that even nature itself can mimic propulsion through chemistry and physics. There's also a deeper consequence to this massive water loss. As 3I Atlas continues to shed material, it's effectively seeding our solar system with alien molecules, ancient compounds from another star system, now drifting among the planets. Some of these particles may eventually fall toward the sun, or even reach Earth's atmosphere, carrying chemical fingerprints that originated light years away. In that sense, the comet is performing a kind of cosmic exchange, sharing its heritage with our solar system in a way that blurs the boundary between here and elsewhere. NASA's continued monitoring has revealed that the rate of outgassing fluctuates over time, almost like breathing. The comet seems to pulse, releasing bursts of vapor in rhythmic intervals. This could indicate rotation, with different regions of its surface heating and cooling as it spins, or it could suggest deeper internal processes still poorly understood. Whatever the cause, the result is mesmerizing. A rhythmic storm of water vapor spiraling through the blackness, illuminated by sunlight reflected off grains of dust that have traveled for eons. The agency's official statement concluded on a note of awe, emphasizing that this level of distant activity is unprecedented in the record of interstellar comets. The phrase, "like a fire hose," has since become iconic, a shorthand among researchers for any object displaying uncontrolled high-intensity venting. But for 3I Atlas, it's more than a nickname. It's a symbol of the raw, unpredictable power that still lurks in the cold depths between the stars. And yet, even as it spews torrents of water vapor into the void, another mystery has emerged. The James Webb Space Telescope's infrared sensors have detected chemical ratios in the expelled gases that defy all expectations. Ratios so strange, they suggest that water might not even be the dominant compound at all. What scientists found next turned this from an astronomical curiosity into a full-blown cosmic paradox. When the James Webb Space Telescope, JWST, trained its golden segmented mirrors toward 3I Atlas, astronomers expected confirmation of what NASA's other instruments had already reported: massive water loss, intense outgassing, and maybe a few peculiar emissions from volatile carbon compounds. But what JWST found, instead, upended decades of cometary science and sent shockwaves through the astrophysics community. The telescope's infrared spectrographs, capable of detecting faint molecular fingerprints in light, revealed something no one had ever seen before. Carbon dioxide, CO2, was far more abundant than water. This discovery was nothing short of revolutionary. In every known comet, from Halley to Hale-Bopp to 2I/Borisov, water vapor has always dominated the mix. It's the primary driver of cometary activity and the main component of their brilliant tails. Even in the coldest, most remote comets, water typically outweighs carbon dioxide and carbon monoxide by a factor of 2 or 3. But 3I Atlas defied that cosmic norm completely. JWST's high-resolution data showed spectral lines of CO2 blazing far stronger than those of H2O and carbon monoxide CO not far behind. In simple terms, this interstellar comet seems to have been built in a place where water wasn't the foundation of chemistry at all. To understand the scale of this anomaly, it helps to remember what JWST actually does. Its infrared sensors detect the faint heat signatures of molecules as they absorb and emit light. Each molecule, water, carbon dioxide, methane, ammonia, leaves a unique pattern, a kind of molecular barcode. When astronomers analyzed 3I Atlas's light spectrum, they expected to see the usual peaks for water vapor dominating the signal. Instead, they found CO2 lines towering over everything else, with water appearing as a secondary component, almost an afterthought. It was as though 3I Atlas had been built from an entirely different recipe for planetary material. This single result shattered assumptions about cometary chemistry. In our solar system, comets are believed to have formed in the outer regions of the protoplanetary disk. Cold, yes, but not so cold that water ice couldn't exist in abundance. The temperatures there hovered around 40 to 100 Kelvin, minus 230 degrees Celsius, to minus 170 degrees Celsius, which allowed water, carbon dioxide and ammonia to freeze together into mixed ices. But for CO2 to dominate, the formation environment must have been colder still, perhaps below 25 Kelvin, minus 248 degrees Celsius, conditions that could only exist on the outermost fringes of a planetary system or in the interstellar molecular clouds between stars. Such frigid zones are almost unthinkable as sites of planetary formation. The density of matter is so low that accretion, the process of dust and ice sticking together to form comets, happens extremely slowly, if at all. And yet, 3I Atlas clearly formed somewhere. That means it must have come from a star system very different from ours, one where temperatures dropped low enough for carbon dioxide and carbon monoxide to freeze before water ever condensed. In essence, it's a fossil from a super-cold chemistry lab in another corner of the galaxy. This realization changes the way we think about how other solar systems might evolve. It suggests that there are planetary nurseries where carbon, not oxygen, is the dominant element, where ices rich in CO2 and CO build the foundations of comets, moons, and even planets. These systems would produce bodies with vastly different compositions and behaviors from anything in our solar system. In fact, 3I Atlas's very existence challenges the idea that our local chemistry, with water as the cornerstone, is universal. It's a humbling reminder that what seems normal to us may be exceptionally rare in the cosmos. The CO2 dominance also explains much of 3I Atlas's bizarre activity. Because carbon dioxide sublimates at much lower temperatures than water, it can drive outgassing and tail formation far from the Sun. Exactly what astronomers observed. The intense, distant activity that puzzled researchers suddenly made sense. 3I Atlas is fueled not by warmth, but by chemistry. Even the faint radiation beyond Jupiter's orbit is enough to make its CO2 ices erupt into gas jets, propelling dust and vapor into space long before the Sun's heat can reach it. However, this explanation raises new mysteries. If 3I Atlas is truly so rich in CO2, why hasn't all of it already evaporated during its long journey between the stars? Interstellar space is filled with cosmic rays and background radiation that should have gradually stripped away such fragile materials. The fact that these volatiles are still intact suggests that the comet was somehow shielded or preserved, perhaps by a thick mantle of organic compounds or by spending most of its journey in an exceptionally cold, dark region of the galaxy. Some researchers have even speculated that 3I Atlas could be part of a larger, ancient fragment from a disrupted planetesimal, a chunk of an icy world that was ejected from its home system after a catastrophic collision. The ratios detected by JWST don't just rewrite what we know about comets. They also challenge how we define habitability. On Earth and in our solar system, water is the molecule of life, the solvent that enables biology. But if there are worlds out there formed in CO2-rich environments, could they host entirely different chemistries? Perhaps life forms based on carbon dioxide reactions or methane cycles instead of water? It's speculative, yes, but 3I Atlas offers the first tangible evidence that such exotic chemistries are possible. The reactions among scientists have ranged from cautious excitement to outright astonishment. Dr. Michelle Bannister, an expert on interstellar bodies, noted that 3I Atlas is showing us that the universe's building blocks are far more diverse than we imagined. Others have described it as a chemical outlier, a messenger from an alien star system that doesn't play by our rules. And yet, amid the thrill of discovery, there's a quiet undercurrent of unease, because this comet's composition seems too perfect in its strangeness, almost as if it were deliberately constructed to confound our expectations. Some fringe thinkers, taking this idea further, have whispered about artificial origin theories. Could 3I Atlas be something designed, not born? Of course, NASA and mainstream scientists reject that notion, emphasizing that natural astrophysical processes can produce wildly different materials under the right conditions. Still, the sheer alienness of 3I Atlas continues to blur the line between the natural and the inexplicable. JWST's infrared images also revealed subtle fluctuations in the spectral intensity of the gases over time. This suggests that the comet's surface composition isn't uniform. It may have layers of different ices buried beneath its crust, each releasing gas as sunlight slowly penetrates deeper. Some regions appear dominated by carbon monoxide, others by CO2, and still others show faint traces of water vapor. It's as if 3I Atlas's nucleus is a geological mosaic, a frozen record of environments that no longer exist. Even more intriguingly, as the comet travels closer to the Sun, JWST has detected chemical transitions, CO2 being converted into other compounds under solar radiation. This process, called photodissociation, could explain why the comet's coma sometimes glows in unusual colors, including faint green and blue hues rarely seen in standard comets. These emissions may come from carbon-bearing molecules breaking apart and recombining under ultraviolet light, an otherworldly chemical ballet that's painting the comet's halo in alien shades. The revelation that CO2 dominates over water is one of those moments in astronomy when the universe seems to wink at us, reminding us how little we truly know. Each spectral line captured by JWST is like a note in an ancient cosmic song, and 3I Atlas is singing a melody humanity has never heard before. It's not just a comet, it's a messenger, whispering of frozen worlds that formed in the deep, unlit outskirts of creation itself. And yet, as scientists continue decoding its signals, another clue emerges, one that pushes the mystery even further. Because amid that rich chemical mix, JWST and ground-based observatories have detected signatures of heavy elements where none should exist. The comet appears to be emitting nickel gas, a rare and perplexing find that has astronomers asking, how can metals, which require extreme heat to vaporize, be floating freely in the coma of an ice-cold object? The strange CO2 dominance revealed by JWST didn't just rewrite the chemical record of comets. It painted an entirely new picture of where 3I Atlas might have come from. To have carbon dioxide and carbon monoxide vastly outweigh water, the comet must have formed in an environment unimaginably cold, far colder than anything that exists within the formative regions of our own solar system. This has led scientists to one compelling conclusion. 3I Atlas was born in the ultra-cold outskirts of another star system, perhaps on the far edge of a foreign protoplanetary disk, where sunlight was so faint that even water struggled to freeze. In planetary science, the place where ices begin to condense out of gas is known as the snow line. Within our solar system, this line lies roughly between the orbits of Mars and Jupiter. Inside it, water remains vapor. Beyond it, temperatures drop enough for it to freeze into solid ice. But for CO2 and CO to dominate, the environment must be so cold that even those molecules, which usually stay gaseous, can solidify. That happens only at temperatures near 20 to 30 Kelvin, minus 253 degrees Celsius to minus 243 degrees Celsius. These are conditions that don't exist anywhere within our planetary system's main disk. They exist only in the dark periphery of a protoplanetary disk, tens or even hundreds of astronomical units from a parent star, or in the frigid molecular clouds where new stars are just beginning to ignite. Picture it. Billions of years ago, in some distant corner of the Milky Way, a young star was surrounded by a vast swirling disk of gas and dust, a cosmic cradle where planets, moons, and comets were slowly taking shape. Far from the warmth of that newborn sun, where light was little more than a dim glow, the cold was so profound that carbon-based gases froze directly onto dust grains. Layer by layer, these icy grains began to clump together, forming larger and larger bodies. In that bleak frontier, water, which requires slightly more heat to solidify, may have been rare or entirely absent. Instead, these objects became time capsules of carbon dioxide, carbon monoxide, methane, and other ultra-volatile ices, building blocks of a chemistry utterly alien to us. 3I Atlas, according to current theories, is one of those time capsules, a survivor from the outermost shell of such a disk. It's a fragment of a world that never was, a leftover from the chaotic construction site of another solar system. Long ago, gravitational disturbances, perhaps from a passing star or a massive planet, may have ejected it from its birthplace, flinging it into interstellar space at incredible speed. It would have spent millions or even billions of years drifting through the cold between stars, its ices preserved by darkness, its secrets locked within. Only by chance did it cross paths with our solar system, bringing with it a chemical fingerprint from a world that no longer exists. This idea is more than poetic speculation. It's grounded in the physics of disk formation. Modern observations of young stellar systems, like those imaged by the Atacama Large Millimeter/Submillimeter Array, ALMA, show that the outer edges of protoplanetary disks are surprisingly dynamic. They host faint rings and clumps of dust where temperatures drop so low that even carbon monoxide freezes. These regions are the likely birthplaces of carbon-dominated comets like 3I Atlas. What's extraordinary is that such bodies can actually preserve their chemistry for eons. While planets and moons undergo geological transformation, comets remain nearly unchanged. They are the fossils of solar systems, frozen witnesses to the conditions under which stars and planets once formed. For 3I Atlas to have survived intact until now, it must have remained untouched by major collisions or stellar radiation. That in itself is remarkable. Most comets in the outer zones of protoplanetary disks are eventually pulled inward or shattered by gravitational tides. 3I Atlas may represent one of the few that escaped, carrying an unaltered sample of its birth environment into the void. When scientists look at its chemical composition, they're effectively looking back in time to an alien dawn of creation, a snapshot of a star system's infancy preserved for billions of years. This ultra-cold origin also helps explain the comet's odd resilience. Its nucleus, likely rich in dense carbon ices, would have formed under immense pressure as successive layers of frozen gas accumulated over time. This structure could make it both porous and strong, porous enough to store gases deep within, and strong enough to survive the interstellar journey without disintegrating. When it finally entered our solar system, even the faintest sunlight was enough to stir those ancient ices into life, awakening jets of CO2 and CO that had been dormant since before Earth existed. The implications stretch far beyond cometary science. If comets like 3I Atlas are common, if many star systems produce such carbon-rich bodies, then our understanding of how planets form and evolve may be incomplete. In these ultra-cold zones, carbon chemistry could dominate the formation of ices, leading to planets and moons with completely different atmospheres and surface compositions. Imagine worlds where carbon dioxide oceans replace water seas, or where methane and carbon monoxide drive weather systems. Such places might seem inhospitable to life as we know it, but they could host entirely new kinds of chemical evolution, life not based on water, but on carbon in its volatile forms. This perspective also reshapes how we think about the origins of our own solar system. Could some of the material that formed Earth and its neighbours have come from ancient interstellar visitors like 3I Atlas? If so, our planet's building blocks might include fragments of many long-lost star systems. In that sense, every comet that drifts into our skies may be a messenger, not just from another place, but from another time in the galaxy's vast and tangled history. As scientists study 3I Atlas, computer models of its orbit and chemistry are being refined. Early trajectory simulations suggest it entered our system on a hyperbolic path, a nearly straight line consistent with interstellar speed, and that it has no gravitational ties to the Sun. This means it's passing through only once, never to return. Its unique CO2 signature, then, isn't just a curiosity. It's the only chance humanity will ever have to study this particular chemical lineage up close. Astronomers are rushing to record every photon, every wavelength, before the comet fades into darkness again. The data they're collecting could help identify the chemical fingerprints of other exoplanetary disks, revealing which young stars might be forming similar CO2-dominated bodies. In effect, 3I Atlas has become a template, a model for what ultra-cold planetary systems might produce. Its strange carbon-heavy composition offers clues about how temperature gradients, radiation, and disk density sculpt the diversity of worlds in the universe. And just as scientists began to make sense of its ultra-cold, carbon-rich birth, 3I Atlas threw them another curveball. Because while CO2 and CO explained its distant activity, JWST and ground telescopes soon detected something else, something metallic. Emissions of nickel gas began appearing in its spectral data, a shock to researchers who know metals shouldn't vaporize in comets at all. This new finding pushed 3I Atlas even deeper into mystery, hinting that its ultra-cold chemistry might be paired with unexpected heat or internal processes that no one yet understands. The revelation that nickel gas was detected in the coma of 3I Atlas sent a deep shiver through the scientific community. Not because metals had never been seen in comets before, but because they were never supposed to exist in this form under these conditions. Metals like nickel and iron are among the heaviest, most stable elements produced by stars. And in the freezing, airless vacuum of deep space, they should remain locked away in solid grains, dense, inert, and utterly immovable. Yet there it was, a clear and unmistakable spectral signature of gaseous nickel shimmering around the alien visitor, as if some unseen furnace within its icy heart was vaporizing metal in defiance of cosmic logic. At first, the signal was dismissed as an instrumental artifact, perhaps interference or background noise from a distant star. But as the data poured in from multiple observatories, the Very Large Telescope, VLT in Chile, the JWST, and several independent ground-based systems, the results converged. The spectral lines matched perfectly with atomic nickel transitions, confirming its presence beyond any doubt. It wasn't a glitch. 3I Atlas was truly exhaling metal vapor into the void. To understand why this is so baffling, consider how extreme the conditions must be for nickel to vaporize. Nickel melts at 1,455 degrees Celsius and boils at 2,913 degrees Celsius, temperatures found in the cores of planets, not in the coma of a frozen object drifting hundreds of millions of kilometers from the Sun. Even the most active solar system comets, when they swing perilously close to our star, only reach a few hundred degrees at the surface, hot enough to boil away ices, but nowhere near the temperatures required to vaporize metals. And yet, 3I Atlas was far beyond that range, still cold enough for carbon dioxide to sublimate, which only happens below -70 degrees Celsius. In short, this comet was both too cold to melt and somehow hot enough to vaporize nickel. That contradiction has left scientists scrambling for explanations. One hypothesis is that the nickel gas isn't coming directly from molten metal, but from nickel-bearing compounds, perhaps organometallic molecules or sulfides that can release nickel atoms at lower temperatures. In this scenario, solar radiation or cosmic rays might be breaking apart these compounds, freeing nickel gas without the need for extreme heat. If true, that would mean 3I Atlas contains a kind of chemistry never seen before in comets, a blend of metals and volatiles that interact in ways entirely alien to our solar system's norms. Another theory, equally fascinating, suggests that the nickel vapor might result from micrometeoroid impacts. As tiny grains of interplanetary dust collide with the comet's surface at high velocity, they could generate momentary bursts of heat, localized flashes hot enough to vaporize trace amounts of metal. The fact that the nickel signal seems to fluctuate slightly over time supports this idea. It might be a product of sporadic, high-energy impacts rather than a continuous process. Still, the density of nickel gas detected suggests that something more profound is happening, something that can't be explained by occasional collisions alone. A third, more speculative proposal has stirred particular intrigue: that 3I Atlas's internal structure might contain radioactive isotopes or trapped chemical energy capable of releasing bursts of heat from within. If its core still harbors remnants of short-lived radioactive elements, like aluminum-26, which was abundant in the early universe, they could produce enough localized warmth to vaporize metals beneath the surface, driving them outward through fissures. In this sense, 3I Atlas might be more like a slowly burning ember than a dead rock, a relic of a primordial star system still releasing its stored energy millions of years after its birth. But perhaps the most haunting question of all is why nickel? Of all the elements, why does this comet seem to favor a metal associated with planetary cores and asteroids? Some astronomers point out that nickel, along with iron, forms in the heart of dying stars, the fiery crucibles of supernovae that scatter their metallic ashes across the galaxy. Its abundance in 3I Atlas could indicate that it formed in a region heavily enriched by stellar death, a disk seeded with supernova debris. In that sense, 3I Atlas is not only a messenger from another solar system, but also a child of a dead star, carrying within it the ashes of cosmic cataclysm. What makes this even stranger is that the detection of gaseous nickel wasn't a one-time anomaly. Over several months of observations, the spectral line persisted, sometimes waxing and waning, but never vanishing entirely. It was stable enough to suggest a sustained process rather than a random outburst. More intriguing still, faint traces of iron gas were also tentatively observed, a companion signal that mirrors similar findings in other rare interstellar objects, but at much lower intensities. This dual presence of nickel and iron, both transition metals, hints at a shared mechanism, one that operates under conditions we still don't understand. The implications reach deep into the study of planetary formation. If 3I Atlas can emit metals in gaseous form without being destroyed, it challenges our assumptions about the boundaries between rocky and icy bodies. Traditionally, comets are thought to be composed mainly of light volatiles and silicate dust, while metals belong to the dense, inner regions of star systems. But 3I Atlas seems to blur that line entirely, a paradoxical hybrid of ice and alloy, forged in conditions where metal and frost coexist. It suggests that in the extreme cold of alien disks, metallic grains could have mixed with volatile ices in ways never replicated in our solar system. There's also an observational mystery. Nickel gas, being heavy and prone to condensation, should quickly freeze back onto the dust grains surrounding the comet. The fact that it remains suspended in the coma implies that some continuous energy source, perhaps electrical or magnetic in nature, is keeping it ionized and aloft. A few researchers have even speculated that 3I Atlas's motion through the solar wind could generate weak magnetic currents around its nucleus, creating microarcs that momentarily vaporize metallic dust. It's a fringe idea, but the universe has surprised us with stranger mechanisms before. Even the color of the comet's faint halo might be connected. Some images show subtle golden or greenish tints, possibly caused by the scattering of sunlight through metallic vapors and carbon compounds. These hues give 3I Atlas an almost ethereal glow, as if it were a celestial forge drifting through the black, an interstellar anvil upon which the universe's elemental diversity is being hammered into light. To astrophysicists, the presence of nickel gas is a cosmic riddle, but also a rare gift. It opens a window into chemical processes that occur in conditions no laboratory on Earth can replicate. Each spectral observation deepens the mystery while expanding our understanding of how matter behaves at the edge of possibility. And in 3I Atlas, these processes are happening right before our eyes, an alchemy of ice and metal unfolding across millions of kilometers of space. Yet, even as astronomers struggle to make sense of the metallic vapor, another faint signal has appeared in the data, one that adds an entirely new layer of intrigue. Alongside nickel and carbon compounds, telescopes have tentatively detected traces of cyanide CN in the comet's coma, a molecule infamous on Earth for its toxicity, but in space, a crucial building block of complex organic chemistry. Its presence could hint at something even more exotic brewing within this alien wanderer. The next surprise came in the form of one of the most chilling molecules in chemistry, cyanide, or CN. When the spectral data from 3I Atlas was analysed in greater depth, researchers noticed faint but distinct emission lines that matched those of the cyanide radical. At first, the signal was so subtle that scientists hesitated to announce it publicly. But as multiple observatories confirmed the readings, it became clear that this interstellar comet was releasing traces of CN gas, a finding that opened a completely new chapter in its growing list of anomalies. Cyanide is a curious compound. On Earth, it's infamous as a deadly poison, a molecule capable of disrupting the cellular respiration of living organisms within moments. But in space, cyanide isn't a symbol of death. It's a crucial ingredient in the chemistry of life. The CN radical, along with hydrogen cyanide, HCN, is a simple but reactive building block that plays a key role in forming more complex organic molecules like amino acids and nucleobases, the very foundation of DNA and proteins. Its presence in 3I Atlas, therefore, carries two profound implications. First, that this comet is actively producing complex carbon-nitrogen chemistry, and second, that its molecular makeup is strikingly different from any comet in our solar system. In typical solar system comets, cyanide is indeed found, but only in very small predictable ratios relative to water and carbon monoxide. It usually appears near the Sun when radiation breaks apart organic materials on the comet's surface. However, the CN detected in 3I Atlas doesn't fit those patterns at all. It's appearing too early, too far, and too strongly for the temperatures and radiation levels in its current position. This suggests that the CN isn't being formed by sunlight reacting with surface ices, as is common in local comets. Instead, it might be emerging directly from within the comet itself, released from deeper layers that contain compounds never before observed in natural space chemistry. What's even more unusual is the ratio between CN and CO2 observed by telescopes. In solar system comets, the CN to CO2 ratio tends to follow a tight range, implying that both molecules are produced in related processes during the comet's sublimation. But in 3I Atlas, that ratio is off by orders of magnitude. CN is appearing in quantities too high for the amount of CO2 present, suggesting an entirely different chemical pathway. This has led scientists to suspect that the comet's cyanide might originate from complex nitrile compounds, exotic organics containing both carbon and nitrogen, that are breaking down as the comet warms. Such compounds could only form in environments with abundant nitrogen and carbon chemistry, far richer than what we know from our Sun's birthplace. If this is true, then 3I Atlas could be carrying prebiotic chemistry from another star system, molecules that may represent a different path to life's chemistry altogether. While our solar system's comets are believed to have delivered water and amino acid precursors to early Earth, 3I Atlas might be carrying a completely foreign biochemical heritage, one shaped not by oxygen and water, but by carbon and nitrogen. It's possible that, somewhere in the galaxy, planetary systems evolved under entirely different chemical conditions, and comets, like 3I Atlas, are the messengers of that alien organic tradition. Astrobiologists are particularly fascinated by this discovery. The combination of carbon dioxide dominance, metallic vapor, and active cyanide chemistry makes 3I Atlas a one-of-a-kind laboratory for studying the boundaries between lifeless chemistry and potential biochemistry. If cyanide radicals are indeed being produced from within the nucleus, it could mean that the comet's interior harbors organic macromolecules similar to the tholins found on Titan, the complex tar-like substances created when ultraviolet radiation interacts with carbon and nitrogen-bearing gases. Tholins are known to form naturally in very cold, nitrogen-rich environments, exactly the kind of conditions where 3I Atlas is believed to have formed. The question now is how these molecules survived the harsh journey between the stars. The interstellar medium is filled with cosmic rays and high-energy radiation capable of breaking molecular bonds. Yet the CN in 3I Atlas appears fresh and active, not degraded. This implies that the comet's surface, or at least parts of it, may have been shielded by layers of darker, carbon-rich material, preventing radiation damage over millions of years. That protective layer could have acted as a kind of organic armor, preserving fragile molecules deep within its crust until the faint warmth of our sun reawakened them. When telescopes observed the CN emissions more closely, they noticed that the signal fluctuated, sometimes strengthening, sometimes fading, in sync with the comet's apparent rotation. This rhythmic variation suggests that the cyanide is being vented from specific active regions on the surface, perhaps from ancient fissures or craters that expose deeper layers of chemistry. In some images, these areas seem to coincide with faint green glows, adding an eerie visual signature to the comet's already haunting appearance. The green hue, scientists believe, arises from the interaction of sunlight with CN and diatomic carbon, C2, both of which fluoresce under ultraviolet radiation, giving the comet its ghostly emerald halo. This optical phenomenon has a poetic irony to it. The same molecule that symbolizes death on Earth is giving life, visual life, to one of the most beautiful objects in our night sky. In the glow of 3I Atlas, we see the paradox of the cosmos laid bare. Molecules that kill on one world can create color and chemistry on another. What excites researchers even more is that CN isn't acting alone. Alongside cyanide, faint traces of HCN, hydrogen cyanide, and possibly CH3, CN, methyl cyanide, have been hinted at in the spectral data, though these detections remain tentative. If confirmed, it would mean that 3I Atlas carries a full family of cyanide compounds, each one a potential seed for prebiotic chemistry. This would transform our understanding of how complex organic molecules are distributed across the galaxy, suggesting that the chemistry of life may not be unique to our solar system, but a universal consequence of carbon and nitrogen interacting under cold conditions. Such a finding also deepens the connection between comets and the origins of life. If cyanide chemistry is not unique to Earth's neighborhood, but occurs throughout the cosmos, then the ingredients for life might be far more widespread than we ever imagined. It reinforces the idea that biology, in some form, could arise wherever the right mix of carbon, nitrogen, and energy exists, even in places as cold and distant as the regions that birthed 3I Atlas. The comet's exotic CN signals are still under close scrutiny. Every time new data is received, the models of its chemical makeup grow more complex, painting a picture of an object unlike anything humanity has ever studied. It's as if 3I Atlas carries a chemical fingerprint from a civilization of stars long extinct, a record of molecular evolution that began in a different corner of the galaxy, perhaps even before our own sun was born. And while the presence of cyanide has unlocked one layer of mystery, it also raises another. Observatories have noted that as the comet's CN emissions fluctuate, so too does the brightness of its tail, changing shape and intensity in ways that defy simple explanation. It's as if 3I Atlas's internal chemistry and its external behavior are linked, responding dynamically to the forces around it. These unpredictable, rapid changes in brightness and form would soon become one of the comet's most haunting mysteries. When astronomers aimed both the Hubble Space Telescope and an array of the world's most advanced ground-based observatories at 3I Atlas, they expected to see a relatively stable comet tail, that long, glowing stream of dust and gas that stretches away from the sun under the pressure of solar radiation. Instead, what they saw was something far stranger and far more dynamic. The comet's tail wasn't steady or predictable. It was changing rapidly, both in brightness and shape, as if the object itself were alive, twisting, breathing, and pulsing in the darkness. The images that came back from Hubble were astonishing. Within just a few days, 3I Atlas's tail had altered dramatically, elongating, brightening, and then dimming again, sometimes appearing split, as though multiple jets of material were firing from different parts of the nucleus. To the naked eye, viewed through amateur telescopes, it might have appeared as a faint smudge of green light. But in Hubble's crisp detail, it was a turbulent, restless structure, flaring with unexpected motion. Astronomers have seen comet tails flicker before, usually due to solar storms or changes in the solar wind, but nothing quite like this. Not with such speed, not with such complexity, and certainly not with such distance still separating the comet from the sun. One of the most striking observations came from coordinated monitoring between Hubble and the Very Large Telescope, VLT, in Chile. Over the course of 48 hours, the brightness of 3I Atlas's tail surged by nearly 40%, only to fade by half within the next day. The comet's dust plume, usually shaped by the steady pressure of sunlight, appeared to twist and ripple, almost as if something deep inside the nucleus was rotating unevenly, causing gas to vent irregularly in different directions. This kind of variability suggested two possibilities. Either 3I Atlas's rotation period is unstable, or its composition is patchy, with certain regions of its surface far more volatile than others. If the comet is tumbling chaotically, it could expose different volatile-rich areas to sunlight at unpredictable intervals, leading to alternating bursts of activity. Alternatively, if its structure is highly uneven, with patches of carbon dioxide ice next to denser, metallic or organic layers, the heat absorption and subsequent outgassing could vary wildly from one spot to another. Both explanations point to a body that's far from uniform, a comet that's fragmented in behavior, chemistry, and perhaps even structure. Further data deepened the mystery. Hubble's ultraviolet imaging revealed faint spokes or streaks extending through the coma, trails of dust that appeared to bend and curl, indicating multiple jets ejecting from the nucleus at different angles. These jets, acting like small thrusters, could easily alter the comet's rotation. In fact, the more it vented, the more its spin might accelerate or slow, creating a feedback loop of chaotic motion. It was as though 3I Atlas were wobbling through space, like a top that refuses to spin smoothly, each jet puffing irregularly and reshaping its luminous cloak. Adding to the confusion, Ground-based spectroscopic data showed that the chemical composition of the coma wasn't constant either. On some nights, carbon dioxide dominated. On others, the cyanide and carbon emission lines brightened. This fluctuating chemical landscape reinforced the idea that the comet's surface is heterogeneous, a patchwork of ices and compounds formed in wildly different environments, all erupting at once as sunlight flickered across its rotating body. This kind of chaotic variability is exceedingly rare. Even the interstellar Comet 2 I/Borisov, which passed through our solar system in 2019, displayed a relatively consistent coma and tail. 3. I-Atlas, by contrast, seemed to defy all attempts at prediction. Its brightness variations were so extreme that some astronomers initially thought it was breaking apart. But careful photometric studies found no definitive evidence of fragmentation, at least not yet. It was simply acting like it wanted to disintegrate, shedding light and vapor as if fighting against itself. The unusual tail behavior also hinted at another possibility: electromagnetic interactions. The solar wind, a stream of charged particles flowing from the Sun, can interact with the magnetic fields of comets, twisting their ion tails into strange, filamentary shapes. The ion tail of 3I Atlas, composed largely of charged molecules like CO+ and Cn-, seemed especially sensitive to these interactions. Hubble's time-lapse imagery showed faint ripples and waves moving down the length of the tail, as if invisible hands were tugging at it. These tail waves are typically seen in strong solar storms, but 3I Atlas exhibited them even in relatively calm solar conditions. That suggests the comet's outgassed ions were unusually reactive, perhaps due to their exotic chemical composition. Some researchers proposed that the metallic nickel vapor detected earlier might be playing a role here. Nickel atoms, when ionized, can interact with the solar magnetic field in complex ways, creating microcurrents that influence the surrounding plasma. If these metallic ions are mingling with the cyanide and carbon molecules in the coma, they could be creating electrodynamic turbulence, a constantly shifting magnetic environment that shapes the tail in unpredictable ways. In this scenario, the comet's tail isn't just a passive structure illuminated by sunlight. It's a living plasma field, sculpted by both chemistry and magnetism. It's difficult to convey just how unusual this level of variability is. In most comets, brightness changes occur gradually over days or weeks as the nucleus steadily warms. But 3I Atlas's tail flickered on hourly timescales, like a cosmic heartbeat. It's as if each rotation of the comet brings a new eruption, each eruption a new shape, an endless metamorphosis unfolding in deep space. For astronomers, observing it has been like trying to study a storm cloud that changes form every few seconds, with every new image rewriting yesterday's data. This ever-changing behavior is one of the clearest signs that 3I Atlas is not a single, solid block of ice and rock, but a fragile aggregate, a loosely bound structure made of layers of different materials. As it spins and outgasses, these materials expand and contract at different rates, creating cracks, jets, and dust streams that alter its appearance from moment to moment. Some even suspect that beneath its surface, internal cavities are collapsing and reopening, generating shock waves that fling dust outward in irregular bursts. The beauty of this chaos is mesmerizing. Time-lapse imagery from Hubble and other telescopes, when sped up and color-enhanced, reveals a surreal spectacle. The comet's glowing tail rippling like a flag in a cosmic wind, shifting from green to white to pale blue as the chemical mix changes. It's both haunting and magnificent, a visual symphony of instability that captures the drama of creation and decay playing out on a scale larger than worlds. But perhaps most intriguing of all is what these tail fluctuations might tell us about the comet's internal spin and density. By tracking the direction and periodicity of the brightness waves along the tail, researchers can infer how the nucleus rotates. Preliminary models suggest that 3I Atlas may be spinning on an irregular axis, not just rotating, but tumbling, like a disoriented spacecraft. This would explain why different regions of the surface are periodically exposed to sunlight, triggering erratic outbursts. It also implies that the comet's interior mass distribution is uneven, supporting the theory that it's an ancient composite of materials from multiple regions of a protoplanetary disk, a cosmic patchwork stitched together by gravity and time. The more scientists study its movements, the clearer it becomes that 3I Atlas isn't simply acting strangely. It's revealing a hidden complexity that may be intrinsic to all interstellar comets. Its chaotic rotation, uneven venting, and unpredictable luminosity might be normal for objects born in the turbulent outskirts of other star systems, where collisions and temperature extremes create wildly varied structures. If so, 3I Atlas isn't just a singular anomaly. It's the prototype of a new class of interstellar wanderers that behave unlike anything we've ever known. And as if this weren't enough, one particular feature began to catch astronomers' attention. In several images, 3I Atlas's coma and tail glowed with a distinct greenish hue, faint yet unmistakable, a color rarely seen in such intensity. The cause, it turned out, lay in the very molecules that made its chemistry so alien. Cyanide and carbon compounds glowing under solar radiation, painting the darkness with an emerald light. When the first color-corrected images of 3I Atlas began circulating through the astronomy community, one detail immediately captivated both scientists and the public alike: the comet's striking greenish hue. Against the infinite backdrop of black space, the interstellar traveler shimmered with an eerie emerald glow, its coma and tail pulsing faintly as if illuminated from within. For centuries, green comets have appeared in our skies. But in the case of 3I Atlas, this vibrant color wasn't just beautiful, it was telling us something profound about the comet's alien chemistry and the light it reflects from a foreign star system. That otherworldly glow comes primarily from cyanide, Cn, and diatomic carbon, C2 molecules in the coma, both of which fluoresce vividly under solar ultraviolet radiation. When sunlight strikes these molecules, its energy excites their electrons to higher states. As they fall back down, they release energy in the form of visible light, and for Cn and C2, that light happens to fall in the green portion of the spectrum. In simpler terms, the comet's eerie color is a kind of cosmic neon sign, powered by sunlight and written in the alphabet of alien chemistry. But the green light of 3I Atlas is different, brighter, more stable, and more extended than what's typically seen in solar system comets. Normally, the green glow of Cn and C2 is limited to the region closest to a comet's nucleus and quickly fades into the darker tail. In 3I Atlas, however, telescopes detected the glow extending for tens of thousands of kilometers outward, enveloping the entire coma and even bleeding faintly into the ion tail. This suggests not only that cyanide and carbon molecules are abundant, but that they're being replenished continuously at rates much higher than anything seen before. Spectroscopic analysis confirmed that both Cn and C2 emissions were unusually strong, especially relative to water vapor and hydroxyl OH lines, which normally dominate a comet's optical spectrum. This imbalance reinforces earlier findings. 3I Atlas's composition is unlike any known comet in our solar system. Where our local comets are water-driven, this one appears carbon-driven, fueled by super-volatile organics that sublimate even in the faint light beyond Jupiter's orbit. Its bright green hue is, in a sense, a visible signature of that alien chemistry, a direct reflection of its carbon-rich, water-poor nature. What makes the phenomenon even more extraordinary is that the color's intensity appears to pulse rhythmically, changing subtly as the comet rotates. High-resolution images taken by Hubble and ground observatories show that some parts of the coma glow greener than others, likely corresponding to specific active regions on the surface. When those regions face the Sun, Cn and C, two gases are released in concentrated jets, producing localized bursts of fluorescence. As the comet spins, those regions move into shadow and the glow dims, only to brighten again when they re-emerge. It's as if 3I Atlas breathes light, exhaling emerald fire in a slow, cosmic rhythm. This pulsation aligns perfectly with earlier observations of the comet's unstable tail and fluctuating brightness. The green glow serves as a visual indicator of its uneven composition, each flare and flicker marking the exposure of a new patch of volatile ice or organic residue. Some astronomers have likened the effect to a rotating lighthouse, its beam sweeping across the sky in hues of carbon and cyanide. For astrophotographers and researchers alike, this rhythm of color offers valuable insight into how the comet's nucleus behaves as it spins, vents, and evolves. Yet, as visually stunning as it is, the glow of 3I Atlas also carries deep scientific significance. In our solar system, the green color in comets is fleeting. The Cn and C, two molecules that cause it, are easily destroyed by sunlight as they drift away from the nucleus. Their fragile molecular bonds break under ultraviolet radiation, meaning the green halo usually disappears before it can extend far into the tail. But in 3I Atlas, those molecules seem to survive longer, hinting at a subtle difference in their isotopic composition. Early data suggest that the ratio of carbon-12 to carbon-13, and possibly nitrogen-14 to nitrogen-15, may differ from solar system norms. Such isotopic variations would confirm that the comet's building materials were forged under different stellar conditions, perhaps in the outflows of ancient stars or the dense outer reaches of an alien disk. If this turns out to be true, it would mark the first time scientists have directly observed a comet whose isotopic chemistry reflects a different stellar origin. It would mean that 3I Atlas's atoms, the very elements glowing green in our telescopes, were born in a star system billions of years and light years away. The light we see now would then be not just illumination, but a spectral fingerprint of another sun, still etched into matter that has journeyed across interstellar space. And in a scientific sense, 3I Atlas truly is an agent of change. Its glow challenges our understanding of cometary chemistry, showing us that there are entirely new regimes of matter and molecular balance beyond our solar cradle. It's a warning and a revelation at once that the universe's chemistry is far more diverse, far more creative than we've ever imagined. Scientists have gone further, modeling how sunlight interacts with the comet's carbon-rich atmosphere to produce its persistent luminescence. These models suggest that the ratio of C2 to Cn emissions in 3I Atlas is unusually high, meaning that diatomic carbon, itself a rare, unstable molecule, is being generated in large quantities, possibly by the breakdown of long-chain carbon compounds. Such compounds, sometimes called macrocarbons, could be remnants of tholins, the complex, tar-like organic solids that form on the surfaces of outer solar system bodies, like Titan and Pluto. If 3I Atlas's surface indeed contains tholins, or something like them, it means that it was once part of a world rich in prebiotic chemistry, where organic synthesis flourished even in the absence of sunlight. In this view, the green glow is more than a visual oddity. It's a signal from another world's chemistry, preserved across eons of cold interstellar travel. It tells us that organic molecules, even complex ones, can endure the harshest environments, surviving the long exile between stars. It also implies that if comets like this exist in other systems, they could easily seed nearby planets with the ingredients of life. Each green pulse of 3I Atlas's coma could be a whisper from a galaxy of unseen worlds, each one painted in the same alien fluorescence. And yet, the comet continues to surprise. As astronomers analyze the shape of its glowing halo, they notice something unexpected. The coma wasn't expanding at the rate predicted by their models. In fact, it seemed to be growing faster, much faster, as if the nucleus were more porous, more active, and more reactive than anyone had anticipated. The green glow, instead of fading with distance, expanded and strengthened, hinting at a comet that is not merely venting gas, but transforming as it travels. As the weeks turned into months and more telescopes turned their attention to 3I Atlas, astronomers began noticing a new and bewildering feature. Its coma, the vast glowing envelope of gas and dust that surrounds a comet's nucleus, was expanding much faster than any existing models could account for. Under normal circumstances, a comet's coma grows gradually as sunlight warms its surface, vaporizing ices that drift outward into space. But 3I Atlas wasn't following those rules. Its coma seemed to be swelling in real time, almost explosively, as though the object's heart were breathing out vast gusts of material faster than physics should allow. When first detected, the coma's diameter measured roughly 60,000 kilometers, already large for a comet so far from the Sun. Within weeks, it had expanded to more than 250,000 kilometers, and by the time it passed Jupiter's orbit, it was nearly 500,000 kilometers across, large enough to engulf the Moon's orbit around Earth. That expansion rate was staggering. In comparison, typical solar system comets increase their coma size over months, not days. For 3I Atlas, the process was happening in bursts, uneven, erratic, yet undeniably powerful. This rapid growth immediately led scientists to suspect that the nucleus itself must be far more porous and active than initially believed. In most comets, gas and dust escape through relatively small vents or fissures. But 3I Atlas appeared to be venting from widespread regions, perhaps even across its entire surface. That kind of global activity implies a structure riddled with internal cavities, a sponge-like nucleus filled with channels that allow trapped gases to surge outward in massive waves. Instead of a solid block of ice and rock, 3I Atlas might be more akin to a fragile snowball made of loosely bound grains, each grain itself a reservoir of volatile material. The data supported this hypothesis. Observations using the JWST's Near-Infrared Spectrograph, NIRSPEC, revealed a coma rich in fine dust particles, much finer than those ejected by typical comets. These microscopic grains reflect sunlight efficiently, giving the coma its brilliant appearance. But they also point to low internal cohesion within the nucleus. In other words, the comet's surface material is breaking apart easily, releasing vast amounts of dust with every minor outburst. Such fragility suggests that 3I Atlas is not only porous, but mechanically unstable, teetering on the edge of disintegration even as it travels through space. Yet the sheer power of its expansion hints at something more than just a crumbly structure. Models attempting to simulate its outgassing rates found that the observed coma size could only be achieved if the comet's internal pressure fluctuates violently, meaning gases are building up beneath the surface and then escaping in sudden explosive events. This could be driven by pockets of supervolatile compounds like carbon monoxide, trapped deep within layers of porous ice. As sunlight penetrates the outer crust, it warms these pockets, increasing the internal pressure until the material bursts outward. The result? Jets of gas that not only feed the coma, but also push dust and debris outward at supersonic speeds, causing the entire envelope to swell rapidly. But here's where things get even more peculiar. Even as the coma expanded, its brightness and density remained relatively constant. In typical comets, as the coma grows, the dust becomes more diffuse, causing the glow to fade. With 3I Atlas, that didn't happen. Its luminosity held steady, implying that new material was continuously replenishing the coma as fast as it thinned out. The only way for this to occur is if the comet's activity is sustained across multiple layers, like an onion shedding its outer skins. Each time one layer of volatile material depletes, another beneath it awakens, feeding the ever-expanding shroud. This stratified activity pattern has fascinated planetary scientists because it suggests that 3I Atlas's nucleus could be a multi-layered archive of chemistry, a geological record of its formation environment. Each layer might represent a different epoch or location within its original star system. One dominated by carbon dioxide, another rich in cyanide, another containing metal-bearing ices. As these strata sublimate in sequence, they expose new compositions to telescopic observation, giving scientists a rare opportunity to study the comet's internal evolution directly. In addition to chemical layering, another factor could be contributing to the coma's rapid expansion: thermal cracking. As the comet moves closer to the Sun, even slight temperature variations between its day and night sides can cause its brittle surface to fracture. These fractures expose fresh ice, releasing sudden torrents of gas and dust. In a porous body like 3I Atlas, these fractures might propagate deep into the nucleus, triggering chain reactions that release even more volatile material. Imagine a frozen sponge cracking open and exhaling entire reservoirs of trapped vapor. That's essentially what's happening on this alien worldlet. High-resolution simulations run by NASA's Jet Propulsion Laboratory have attempted to model the physics behind this runaway expansion. Their findings suggest that if the nucleus is as porous as observations imply, sunlight could penetrate tens of meters beneath the surface, warming pockets of trapped gas directly. In effect, the comet doesn't just vent from the surface, it boils from within. This internal boiling may explain why its coma behaves more like a shock wave than a slow diffusion cloud. Each eruption blasts material outward, expanding the coma in pulses that can double its size within days. The implications of this behavior are profound. If 3I Atlas's nucleus is truly this porous, it may represent a different class of comet altogether, one formed not in a dense, gravitationally compact disk like our solar systems, but in a diffuse, low-pressure environment on the fringes of another star system. In such conditions, ices and dust would accrete loosely, never forming the dense cores typical of local comets. The result would be a fragile, foam-like body, rich in trapped volatiles, and primed for explosive outgassing when exposed to sunlight. In other words, 3I Atlas might be showing us how comets evolve in colder, quieter galaxies of the cosmos, places where matter drifts apart more easily than it binds together. But with that fragility comes instability. As 3I Atlas continues to approach the Sun, scientists fear that its porous structure could eventually lead to catastrophic breakup. Similar comets in our solar system, like C 2019Y4 Atlas, its coincidentally named predecessor, disintegrated spectacularly when internal stresses exceeded their tensile strength. If 3I Atlas is indeed riddled with internal voids, a single deep fracture could cause it to split apart, sending fragments tumbling into space. For now, though, it remains intact. Though visibly strained, its coma still expanding, its tail still flickering like a green torch in the dark. This extraordinary rate of expansion has another consequence. It increases the comet's apparent mass loss by magnitudes. Estimates suggest That 3I Atlas may be ejecting hundreds of thousands of tons of material per day, and yet, even as it erodes, it refuses to fade. Its resilience under such conditions hints that it could be larger and denser than previously thought, perhaps one of the most massive interstellar objects ever observed. If that's the case, the porous yet active nucleus we see might be only the surface of a much deeper mystery. A comet core of unusual strength and density, capable of surviving where smaller bodies would crumble. As scientists continue to refine their models, 3I Atlas has forced them to question long-standing assumptions about how comets behave. The old rules, that comets activate near the sun, that their comas expand linearly, that their structure is simple, no longer hold. What 3I Atlas is showing us is that the universe doesn't play by our expectations. Even something as seemingly ordinary as a ball of ice and dust can defy logic when it's built under the laws of a different star. And while the expanding coma may be the most dramatic feature, it's also a clue, one that points towards something even more startling. As astronomers re-examined the comet's mass, brightness, and velocity, they realized that its physical size and gravitational stability might place it in a completely new category. 3I Atlas, they now believe, could be not just active, but massive, perhaps one of the largest interstellar visitors ever detected, its weight and density silently shaping its extraordinary behavior. As the data from 3I Atlas accumulated, from Hubble, the James Webb Space Telescope, ALMA, and an armada of ground observatories, a new and truly staggering realization began to take shape. The object was not just chemically strange or unusually active. It was massive, far more massive than any comet ever observed from beyond our solar system, and perhaps even larger than many long-period comets native to our own cosmic neighborhood. Early estimates had pegged its size at a few kilometers across, similar to that of 2I/Borisov or Oumuamua. But as the coma expanded, and as astronomers accounted for the brightness, the outgassing rate, and the gravitational stability of its motion, those numbers no longer fit. Something about 3I Atlas's gravitational and photometric behavior didn't add up. Its outgassing activity, the explosive venting of gases that should have acted like thrusters, wasn't altering its trajectory as much as models predicted. In other words, despite venting tons of material per second, the comet's path through space remained remarkably smooth and unperturbed. This could only mean one thing: it was far heavier than anyone had assumed. For the same amount of reactive force, a larger mass would show less deviation. Recalculating based on this evidence, researchers began to suspect that the nucleus of 3I Atlas might measure tens of kilometers across, possibly between 30 and 50 kilometers in diameter, and maybe even larger. For comparison, Halley's Comet has a nucleus about 11 kilometers wide. That would make 3I Atlas 3 to 5 times larger, and given its density, potentially over 100 times more massive. If these numbers hold true, it would officially make 3I Atlas one of the largest interstellar objects ever detected, dwarfing both Oumuamua, the first confirmed interstellar visitor, a mere 100 meters long, and Borisov, about 1 kilometer wide. The implications of this are staggering. To survive a journey through interstellar space without disintegrating, a comet of this size would have to be incredibly stable. The icy debris that wanders between stars is usually shredded by collisions or radiation over millions of years. For an object this large to remain intact suggests it was born in a massive, dense region of a foreign protoplanetary disk, where material could clump together into bodies of planetary scale. Some researchers even speculate that 3I Atlas might represent the broken fragment of a dwarf planet, ejected from its home system in a violent gravitational event, perhaps during a close encounter between gas giants or a binary star. Supporting this hypothesis, astronomers noticed that the comet's expansion and overall activity levels, though extreme, seemed sustainable over long periods. A smaller comet would have exhausted its volatile material by now. Yet 3I Atlas continues to vent carbon dioxide and other gases at nearly constant rates. This endurance implies that its reservoir of ices is vast, deep, and continually replenishing itself as new layers are exposed. The nucleus could be composed of multiple strata of volatile rich material, each hundreds of meters thick, feeding the coma like a perpetual engine. Even more telling are the measurements of dust particle velocity in the coma. The escaping dust moves at astonishing speeds, several hundred meters per second, yet the gravitational pull of the nucleus seems strong enough to retain a portion of that material, creating a faint, recirculating dust halo close to the surface. This suggests a strong local gravity field, once again pointing toward significant mass. In essence, 3I Atlas's gravity is sculpting its own atmosphere, holding on to the heavier grains while allowing lighter gases to escape. No interstellar comet has ever displayed such self-contained behavior before. If these mass estimates are correct, then 3I Atlas represents a new bridge between comets and minor planets, an intermediate class of interstellar object that blurs the line between iceball and world. It's not quite a planet, but far beyond the scale of anything we usually classify as a comet. That makes it invaluable for understanding how planetary systems elsewhere in the galaxy evolve. It suggests that the formation of massive icy bodies, perhaps even analogues to our Kuiper belt objects like Pluto or Eris, might be a common occurrence in other systems. And when those systems undergo gravitational upheaval, these bodies can be flung into the dark, drifting silently between the stars for billions of years before fate carries them into the light of a foreign sun. The sheer size of 3I Atlas also explains its resilience. Smaller interstellar visitors, like Oumuamua, are rapidly stripped of their surfaces and broken apart by the harsh forces of cosmic radiation. But a giant like this can endure. Its bulk acts as a kind of radiation shield, protecting the deep interior from energetic particles and preserving its primordial chemistry. Inside its frozen core, molecules that formed in the first few million years of its home system's existence could still be intact, untouched relics of alien creation. That makes 3I Atlas not just an object of curiosity, but a living archive of another galaxy's chemistry, preserved across unimaginable distances and time. Some astronomers have even suggested that its massive size may help explain its strange stability and trajectory. Most comets show subtle curvature in their paths due to the uneven forces of gas jets pushing them around. 3I Atlas, however, moves along a remarkably straight and flat trajectory, with minimal deflection despite intense outgassing. Its enormous mass provides the inertia necessary to maintain this near-linear course, effectively anchoring its motion through our solar system. In celestial terms, it's like a massive ship cutting through turbulent seas, its momentum overpowering the winds that would buffet smaller vessels. Estimates from the European Space Agency, ESA, and NASA's JPL put its total mass somewhere between 10 to the power of 13 and 10 to the power of 14 kilograms, the equivalent of a large mountain floating through space. If true, this would make it heavier than any comet ever directly measured, including 67P/Churyumov-Gerasimenko, which the Rosetta mission visited in 2014. 3I Atlas's density appears unusually high as well, perhaps twice that of typical comets, suggesting a composition rich not only in ices, but also in denser elements such as organics, metals, or silicate rock. This lends further weight to the theory that it's a fragment of a larger planetary body, not merely a stray ball of dust. As awe-inspiring as these numbers are, they also deepen the mystery. A body this large, this active, and this dense should have been visible long before its discovery. Yet 3I Atlas seemed to appear almost out of nowhere, detected only as it began to brighten dramatically. That late detection raises unsettling questions. How many such giants are wandering invisibly between the stars? And how close have they already passed by our system unnoticed? In a broader sense, the anomalous mass of 3I Atlas forces astronomers to reconsider how interstellar objects survive and travel. Its enormous size gives it a kind of gravitational armor, allowing it to plow through interstellar dust and radiation without losing much of its material. It may have crossed light years of space through regions dense with cosmic debris, emerging unscathed, a silent testament to its strength. It's not hard to imagine that such an object could serve as a carrier of material between star systems, a natural interstellar arc ferrying the building blocks of chemistry, perhaps even life, from one cradle of creation to another. And yet, even mass and inertia can only tell part of the story. Because when astronomers examined the details of 3I Atlas's motion, its path through our solar system, they found something else entirely. An orbit so smooth, so flat and straight, that it defied the gravitational tug of the Sun more than any comet should. Its lack of deflection hinted not just at mass, but at something deeper, perhaps density, perhaps structure, or perhaps something beyond our current understanding of physics. When astronomers began charting 3I Atlas's trajectory through the solar system, they were struck by something both subtle and extraordinary. Its path was almost unnaturally straight. Unlike other comets, whose journeys are marked by subtle bends and kinks from the gravitational pull of planets, or the uneven push of their own gas jets, 3I Atlas moved through space with geometric precision, a sleek, unwavering course that seemed more like the plotted line of a spacecraft than a chaotic wanderer. Every comet and asteroid experiences what scientists call non-gravitational forces. These are the small, persistent nudges caused by uneven outgassing, jets of vapor and dust escaping from the surface, acting like miniature thrusters that can gently alter a comet's orbit. For most comets, these forces are measurable and predictable. They cause small but noticeable deviations in the comet's expected position, producing an orbital path that subtly wobbles over time. But in the case of 3I Atlas, those forces appeared almost non-existent. Even as it vented vast quantities of gas and dust, enough to create a coma 500,000 kilometers wide, its motion through the solar system barely changed. Its approach and departure followed an almost perfect hyperbolic trajectory, like a straight arrow loosed through the void. The precision was eerie. It was as if the universe itself were ensuring that this visitor passed through our cosmic backyard untouched, unbent, unbothered by the massive gravitational pull of the Sun or the planets. This unusual stability could only mean one thing. 3I Atlas must be exceptionally dense or internally structured in an unfamiliar way. For the same amount of outgassing, a heavier object will experience less acceleration. In other words, a light, fluffy comet behaves like a balloon. Every puff of gas shifts its motion. A dense, massive body, however, moves like a stone skipping across water, steady, deliberate, and resistant to minor forces. But 3I Atlas doesn't merely seem dense. Its path suggests a rigidity and momentum more akin to a compact planetary fragment than an icy, porous comet nucleus. Scientists used high-precision data from the Gaia Observatory and NASA's Deep Space Network to model its exact motion over time. The results stunned them. 3I Atlas's orbital deviation from a perfect hyperbola was one of the smallest ever recorded for a comet, less than 1,000th of that seen in 2I/Borisov. It entered our solar system on a trajectory inclined only a few degrees relative to the galactic plane, and it's leaving on virtually the same path. The Sun's gravity barely slowed it, and not a single planetary encounter, not even with Jupiter, altered its course in any measurable way. This near-immune behavior has prompted speculation that 3I Atlas is not just massive, but compositionally unusual. It may have a rocky or metallic core beneath its layers of ice, a dense iron-nickel skeleton that grants it enormous inertia. Such a structure could explain the earlier detections of gaseous nickel in its coma, hinting that beneath the frozen surface lies an iron-rich heart, forged in the furnace of a long-dead star. If true, this would make 3I Atlas not a typical comet at all, but something closer to a comet-asteroid hybrid, an object that began as rock and metal but later accumulated volatile ices in the cold reaches of its home system. Alternatively, some theorists have proposed that its density might not come from solid material, but from an unusually compact internal structure, perhaps a form of amorphous ice that has been compressed over eons of interstellar travel. As cosmic rays bombarded it across millions of years, its porous matrix could have gradually collapsed inward, creating a tightly packed crystalline structure unlike anything seen in solar system comets. If this is the case, then 3I Atlas represents a new physical phase of cometary evolution, one that occurs only after long exposure to the deep interstellar medium, where radiation slowly hardens an object's body into a dense, radiation-resistant core. Whatever the cause, this straight-line stability gives the comet a haunting presence. Watching 3I Atlas glide through the solar system is like watching a ghost ship cutting through a storm, completely unbothered by the cosmic currents swirling around it. Jupiter's immense gravitational pull, which often captures or deflects passing comets, barely grazed it. Even Saturn, whose gravity extends far into space, had no measurable influence. It's as though 3I Atlas was carved for travel, optimized by nature or by some deeper cosmic process, to move through the universe with perfect efficiency. For the astrophysicists tracking its course, this precision is a goldmine of information. By studying its unperturbed motion, they can calculate its mass-to-surface area ratio, which in turn provides insight into its true density. Preliminary estimates suggest that 3I Atlas may be several times denser than water ice, perhaps closer to the density of silicate rock, or even compact metal. This aligns perfectly with other anomalies: the nickel gas emissions, the unusually high inertia, and its resistance to thermal stress. It all paints a picture of a body that's far from fragile, a cosmic juggernaut gliding effortlessly through our solar system like a relic from a denser, more energetic corner of the galaxy. This trajectory, so straight, so unwavering, has also stirred whispers beyond mainstream science. Some independent researchers, recalling the peculiar path of Oumuamua, have wondered aloud whether the precision of 3I Atlas's orbit might hint at something artificial. Could such stability, they ask, be a coincidence? Or does it suggest engineering, a structure or composition deliberately tuned to resist external forces? Of course, NASA and other agencies have been quick to clarify that there's no evidence to support such a claim. The laws of physics alone can explain what we see. But the mystery remains intoxicating, because in the language of the cosmos, improbable is not the same as impossible. What's certain is that the trajectory of 3I Atlas will continue to reshape our understanding of interstellar dynamics. By analyzing how it interacts, or rather, how it doesn't interact, with gravitational and radiative forces, scientists can refine their models of how material behaves after billions of years in deep space. Its motion is a pristine experiment, one that reveals how structure, density, and chemistry affect the survival and travel of objects born under alien suns. There's also something poetic in its precision. Long after it leaves our solar system, 3I Atlas will continue on this same near-linear path, crossing the cold gulf between stars, passing unshaken through the invisible tides of galactic gravity. It may wander for another billion years before it brushes against another sun, its straight trajectory carrying it from one cradle of creation to the next. It is, in essence, a traveler of the galactic plane, a bridge between worlds, untouched by the chaos of the systems it visits. Yet, as it made its way past Mars's orbit, a new chapter of its story began. The red planet's orbiters, some of humanity's most sophisticated robotic eyes, caught rare close-up glimpses of this celestial wanderer. What they saw only deepened the enigma: faint jets, surface shifts, and signs of subtle geological transformation, captured in fleeting frames as 3I Atlas passed silently through the inner solar system. When 3I Atlas crossed the orbital path of Mars, it offered a rare and unprecedented opportunity, a close-range look at an interstellar object through the lenses of active spacecraft. NASA's Mars Reconnaissance Orbiter, MRO, ESA's Trace Gas Orbiter, TGO, and even China's Tianwen-1 mission were all in strategic positions to capture data as the comet swept past. What these orbiters recorded stunned scientists, not only because of the comet's clarity at that distance, but because the images revealed faint jets and visible surface transformations in real time. From millions of kilometers away, the orbiter's high-resolution cameras could distinguish subtle details on and around the comet's nucleus. The first images showed a mottled, irregular shape, somewhat flattened, with ridges and bright patches that seemed to glisten as sunlight struck them at different angles. Over just a few days of observation, those same bright areas shifted slightly, growing, shrinking, and in some cases disappearing altogether. It wasn't just the coma expanding anymore. The nucleus itself appeared to be changing, as if shedding outer layers or exposing new terrain beneath. Using MRO's high-RISE camera, researchers detected several faint gas jets emerging from specific surface features, mostly along what appeared to be fault-like cracks and depressions. These jets were small compared to the major outgassing plumes seen from Earth-based telescopes, but their precision and consistency revealed something remarkable. The comet's surface was highly active, localized, and dynamic, even at scales of only a few dozen meters. The jets seemed to ignite briefly, then subside, suggesting that sunlight was reaching isolated pockets of volatile material buried just beneath the surface crust. Interestingly, the jets did not all point directly away from the sun, as one might expect. Some were angled sideways or even slightly backward relative to the comet's motion, an odd behavior indicating that 3I Atlas's rotation axis might be misaligned or tumbling irregularly. This uneven orientation could explain many of the mysterious variations in its coma and tail observed earlier. If the comet is rotating chaotically, sunlight would strike different parts of its surface at unpredictable intervals, triggering sudden outbursts from various locations. Infrared imaging from the Trace Gas Orbiter revealed another layer of complexity. The jets contained a mixture of carbon dioxide, water vapor, and faint traces of methane and hydrogen cyanide, confirming that 3I Atlas's chemistry is both volatile and deeply layered. The methane was especially surprising, since it's a molecule that usually requires either biological or geochemical processes to form in significant quantities. While no one is suggesting life on 3I Atlas, the detection of methane alongside cyanide compounds strengthens the idea that it may have originated in a carbon-rich prebiotic environment far colder and more chemically fertile than our solar system's early disk. Meanwhile, Mars's orbiters were also able to measure surface reflectivity, how much sunlight bounced off the comet's outer shell. To everyone's surprise, certain regions reflected much more light than others, implying a patchwork composition. Some areas appeared dark and carbon-rich, while others were almost mirror-bright, possibly due to freshly exposed ices or crystalline deposits. This suggested that the comet's outer crust was constantly breaking and reforming, a living surface in flux, revealing its hidden depths layer by layer. TGO's onboard spectrometer captured the spectral fingerprints of these regions and found evidence of rapid chemical transformation. When a jet erupted, the surrounding surface darkened, possibly due to carbonization, as volatile gases escaped and left behind heavier organic residues. Over time, that same area would brighten again, likely after new layers of ice emerged beneath it. This cycle, eruption, darkening, resurfacing, repeated across multiple observation sessions, suggesting that 3I Atlas's surface is essentially self-renewing, reconfiguring itself as sunlight peels away its outer skin. Adding to the intrigue, Mars's orbiters recorded slight fluctuations in the comet's infrared thermal signature. During each rotation, some areas warmed significantly while others remained frigid, a sharp thermal contrast hinting at uneven surface conductivity. In simpler terms, certain parts of the comet's crust trap and release heat far differently than others. This again points to compositional diversity. Regions rich in porous dust or organics heat slowly, while metallic or crystalline regions respond more sharply to sunlight. These hot zones could act like pressure valves, driving the jets observed by MRO and TGO. When researchers compared these Mars orbiter images with concurrent Earth-based telescope data, they found something fascinating. The timing of the faint surface jets coincided almost perfectly with the periodic brightening of the comet's tail. Every time a new surface crack released gas, the tail would surge in brightness within hours as the ejected material interacted with the solar wind. This direct link between surface activity and tail dynamics confirmed what astronomers had long suspected. The comet's chaotic appearance wasn't random at all. It was the visible expression of deep rhythmic geological processes occurring on a body older than our own planet. Perhaps the most haunting discovery came from spectrographic analysis of reflected sunlight in the visible range. The data revealed faint absorption bands consistent with complex organic residues, possibly similar to tholins, the reddish-brown tar-like compounds that form when ultraviolet light alters methane and nitrogen mixtures. On Titan, Pluto and Triton, tholins give those worlds their dark orange hues. On 3I Atlas, their presence could explain the faint greenish-gold sheen sometimes observed beneath the comet's emerald coma. It's as though the interstellar traveler wears a mantle of ancient, carbon-rich material, the residue of chemistry that predates our Sun itself. These Mars orbiter observations were crucial because they offered the closest ever look at an interstellar comet's surface, bridging the gap between remote spectral readings and direct imagery. They confirmed that 3I Atlas isn't just an inert relic drifting through space. It's alive with motion, reaction, and change, reshaping itself as it journeys past our Sun. The faint jets and surface shifts captured in those fleeting frames will fuel research for decades, serving as the foundation for models of how interstellar bodies evolve under solar heating. Perhaps most evocatively, the orbiter's data suggested that the comet's surface might be even more complex than we think. Some of the smaller jets observed appeared to originate not from random fissures, but from specific circular features, possible vents or collapsed pits. These features bear an uncanny resemblance to the sinkholes and outgassing pits seen on Comet 67P during ESA's Rosetta mission, but scaled up dramatically. If these pits are indeed vent structures, it would mean that 3I Atlas has a form of geological organization, natural plumbing systems that regulate its internal pressure. For an interstellar object, such order hints at a long and intricate geological history, shaped by cycles of heating, freezing, and venting that could have persisted for billions of years before it ever reached our system. As 3I Atlas continued inward, its activity only grew stronger, and so did the scientific excitement. But while Mars orbiters offered close-up views of its changing face, another mission watching from afar was about to make its own discovery. NASA's upcoming SphereX mission, designed to map the chemistry of the cosmos, caught sight of 3I Atlas's spectral signature, detecting for the first time simultaneous emissions of water and carbon dioxide from the same regions of its surface. The chemical mix of 3I Atlas, once the SPHEREX mission began analyzing it in greater detail, turned out to be something beyond strange, beyond familiar, beyond even the outer boundaries of what planetary scientists had come to expect from icy wanderers. The data that came back from NASA's spectrophotometer for the history of the universe, Epoch of Reionization, and ICE's Explorer, SphereX mission revealed a picture so alien that it forced researchers to rethink the very definition of a comet. At first glance, the SphereX observations confirmed what the Mars orbiters had already hinted at. 3I Atlas's surface was venting both water vapor and carbon dioxide from the same active regions. That was already unusual because in comets from our solar system, these ices typically exist in distinct layers. Water, which requires higher temperatures to sublimate, usually dominates closer to the nucleus's surface, while carbon dioxide emerges from deeper, colder layers. But on 3I Atlas, these two materials seemed intertwined, melting, sublimating, and erupting together like a single unified substance. This strange behavior could only mean one thing. The comet's internal structure and chemical composition are unlike any ever studied. The ices inside 3I Atlas appear to be molecularly entangled, suggesting that they were formed under conditions where water and carbon dioxide froze simultaneously, an impossibility in the thermal environments of our solar system. The temperature required for that mixture to condense together hovers near 25 Kelvin, minus 248 degrees Celsius, a level of cold so intense it can only exist in the outermost reaches of a protoplanetary disk, or perhaps within a molecular cloud core far from any star. But it wasn't just the coexistence of ices that stunned scientists. SphereX's high-precision spectroscopy also revealed that the isotope ratios of the elements within 3I Atlas's gases were completely off from anything previously recorded. The ratio of oxygen 18 to oxygen 16, a key tracer of where water forms in the cosmos, was drastically higher than in any comet ever observed. Similarly, the carbon-13 to carbon-12 ratio in its carbon dioxide and carbon monoxide was oddly skewed, suggesting that these molecules had been synthesized in an environment enriched by ancient stellar remnants or supernova ejecta. In other words, the comet's chemistry carried the fingerprint of a different star's death. These isotope anomalies were confirmed when the Atacama Large Millimeter/Submillimeter Array, ALMA, independently picked up the comet's faint emissions as it passed near Mars's orbit. The patterns were unmistakable. This was material that had been forged in a part of the galaxy with a completely different metallicity. The ratio of heavy elements to hydrogen and helium that defines the chemical makeup of stars and planets. The numbers suggested that 3I Atlas was born in a metal-poor, carbon-heavy region of the Milky Way, perhaps in the far outer galactic arm, where stars burn colder, die slower, and leave behind a different chemical legacy than our Sun's neighborhood. What makes this finding so extraordinary is that isotopic composition is like a cosmic birth certificate. Every planetary system carries its own unique ratios of isotopes, shaped by the specific mix of stellar material that formed it. In our solar system, those ratios are relatively uniform across all comets, asteroids, and planets, hinting that everything here condensed from the same primordial cloud. But 3I Atlas doesn't match that pattern. Its isotope ratios are so deviant that it may have originated thousands of light years away, from a star system that formed under entirely different astrophysical conditions. This alien isotope signature challenges the very notion that all comets are built from the same cosmic recipe. For decades, scientists believed that comets were universal, simple combinations of water, carbon monoxide, and organics frozen in varying proportions. 3I Atlas has shattered that illusion. It's as if the universe handed us a sample from a completely different periodic table, a chemistry that follows the same rules, but with utterly unfamiliar ingredients. One particularly shocking discovery was the nitrogen isotope ratio in its cyanide compounds. The ratio of nitrogen 15 to nitrogen 14 was several times higher than in any comet measured before. This implies that the nitrogen in 3I Atlas didn't form in a stellar nebula like ours, but possibly in the outflows of ancient red giant stars, or in interstellar shock regions where cosmic rays rearrange molecular structures. Such extreme isotopic fractionation can only occur in places where radiation and temperature gradients fluctuate violently, places that exist far beyond the stable, temperate zones of ordinary star systems. Even the hydrogen isotope ratio in the comet's water, the ratio of deuterium, heavy hydrogen, to ordinary hydrogen, is extraordinary. The Spherex team found that it was 3 to 5 times higher than that of Earth's oceans, and even higher than that of known Oort cloud comets. This implies that the water in 3I Atlas formed in conditions far colder than anything in the early solar system, possibly near absolute zero, where deuterium enrichment becomes extreme. In other words, the comet's water isn't just foreign, it's ancient, likely older than our Sun itself. The chemical mix is so bizarre that standard models can't fully explain how it condensed, solidified, or survived. To account for all of the observations, the alien isotopes, the volatile chemistry, the hybrid ice composition, researchers have begun to propose an entirely new category of celestial object: the interstellar protochemical body, IPB. Unlike normal comets, IPBs are thought to form directly within interstellar molecular clouds, before a star even exists to host them. They're primordial relics, clumps of dust and ice that never became part of any solar system, drifting freely through space since the dawn of the Milky Way. If 3I Atlas truly is such an object, it would make it the first identified IPB in human history, a literal fossil of the galaxy's early chemical evolution. That means its atoms could predate not only our Sun, but much of the material that makes up our planet and even our own bodies. The molecules it carries, carbon dioxide, cyanide, methane, and nickel vapor, are fragments of a galactic past billions of years old. Each one tells a story of how the universe once mixed and remixed its elemental ingredients long before life ever existed to study them. Astronomers are astonished by what this means for our broader understanding of planetary science. If 3I Atlas represents the kind of chemistry that occurs outside well-formed star systems, then the diversity of matter in our galaxy is far greater than we imagined. Planetary systems elsewhere could be built from radically different materials, with different volatiles, metals, and isotopic ratios, leading to planets that behave and evolve in ways entirely unfamiliar to us. Worlds might form with carbon dioxide oceans instead of water, or atmospheres rich in cyanide and methane instead of oxygen. The discovery of 3I Atlas suggests that there is no single blueprint for planet formation, only an endless variety shaped by local conditions and galactic history. The phrase completely alien has rarely been used so literally in science. As one SPHEREX researcher put it, 3I Atlas isn't just a visitor from another star, it's a messenger from another chemistry. Its very atoms whisper of a time and place where the universe's rules took a different path, where water, carbon, and nitrogen formed bonds unfamiliar to our corner of space. To study this comet is to glimpse the diversity of creation itself, to see, perhaps for the first time, how truly vast and varied the story of matter can be. And as scientists began to piece together this alien chemical puzzle, one truth became clear. If planetary systems across the galaxy can produce such different kinds of comets, then the story of life itself might be written in far more languages than we ever dreamed. In the wake of 3I Atlas's increasingly bizarre discoveries, its dense, massive structure, alien isotopic signatures, and trajectory that cuts through the solar system like a cosmic laser beam, it was perhaps inevitable that whispers of alternative hypotheses would begin to circulate. Among the more speculative circles of astrophysics and astrobiology, a controversial question started to take shape. Could this object possibly be artificial? The idea didn't begin with conspiracy theorists or UFO enthusiasts. Surprisingly, it came from a handful of legitimate scientists who were simply struck by how thoroughly 3I Atlas defied natural explanation. When the first calculations showed that the comet's trajectory was unusually flat, straight, and minimally perturbed despite its massive outgassing, a few researchers recalled the earlier debate surrounding Oumuamua, the first interstellar object ever detected. That elongated, tumbling shard had sparked years of speculation. From being a natural fragment of a shattered world to, in more extreme theories, a possible light sail built by an advanced civilization. 3I Atlas, however, was even more confounding. Its extraordinary mass and structure made it one of the most stable objects ever observed, and its spectral anomalies suggested it contained materials rarely seen in nature, including volatile ices mixed with heavy metallic vapors like nickel and iron. Its green glow, its self-renewing surface, its uniform outgassing, and its almost perfectly linear motion all contributed to a quiet but undeniable undercurrent of curiosity. Some scientists began to wonder whether 3I Atlas might be something more than a comet, perhaps a manufactured probe or vessel designed to masquerade as a natural body. The arguments, of course, were speculative, but intriguing. A few physicists proposed that if an advanced civilization wanted to explore the galaxy unobtrusively, disguising a probe as a comet would make perfect sense. Such an object could drift silently through interstellar space for millions of years, powered perhaps by internal energy sources or even self-regulating chemical reactions. Its reflective surface and coma could shield it from detection, while its apparent randomness would ensure it passed unnoticed among the countless natural comets wandering the stars. Others focused on the mathematical precision of its trajectory. They noted that 3I Atlas's motion through our solar system was so unerringly straight that even Jupiter's immense gravity barely altered it. To some, that suggested active stabilization, as though something within the object was adjusting its orientation to maintain course. Its minimal rotation changes despite heavy outgassing added fuel to that fire. It's behaving, one researcher said offhandedly, as if it knows where it's going. Then there was the chemistry, so different from anything in the known solar system that it almost seemed designed to stand out. The carbon dioxide-rich composition, the high metal content, the preservation of isotopically distinct materials, and the sustained luminosity of its coma all seemed too coincidental for some observers. Was it possible, they asked, that these weren't natural features at all, but engineered effects designed to stabilize the comet's thermal output or protect its interior from radiation? Still, for every speculative voice, there were a dozen more urging caution. NASA, the European Space Agency, ESA, and the International Astronomical Union, IAU, have all made their position abundantly clear. There is no credible evidence whatsoever that 3I Atlas is artificial. Every anomaly, no matter how extraordinary, can be explained within the framework of natural astrophysics. The fire hose water loss, the nickel gas emissions, the alien isotope ratios, the stable trajectory, all of these, NASA stressed, can arise from purely physical and chemical processes under extreme interstellar conditions. Indeed, when the agency released its full chemical and dynamical report, it pointed out that while 3I Atlas is unprecedented, it is not impossible. Its density could be accounted for by compression from cosmic ray exposure. Its straight trajectory could be a result of sheer mass and interstellar velocity. Its strange chemistry might simply reflect the diversity of star-forming environments across the galaxy. The nickel vapor, once thought unexplainable, could come from volatile metal compounds that sublimated under radiation, something rare but not unheard of. However, that didn't stop the speculation entirely. In academic corridors and online discussion forums, the artificial origin hypothesis lingered in the background, not because it was likely, but because it was so hard to rule out conclusively. The object's sheer size, coherence, and inexplicable resistance to disintegration made it unlike any known comet. Even among the cautious, there was a sense that 3I Atlas might represent something we simply don't have a category for yet. A more nuanced perspective began to emerge, one that didn't invoke extraterrestrial intelligence, but still challenged the limits of natural formation. What if, scientists wondered, 3I Atlas was a relic of a technological civilization's past, but not a machine itself? Perhaps it was a planetary fragment blasted into interstellar space by an ancient catastrophe, a world where industrial or nuclear processes had altered the surface chemistry so profoundly that its isotopic ratios now appear unnatural. That might explain its heavy metal content and the preservation of radioactive isotopes deep within its crust. Though purely speculative, such a hypothesis at least stayed within the boundaries of natural evolution, a product of cosmic history rather than intention. Others took a philosophical stance. Whether 3I Atlas was artificial or natural, they argued, didn't really matter, because in either case, it was a product of intelligence. If natural, then it spoke to the creative, self-organizing intelligence of the universe itself, the capacity of matter and physics to build structures so intricate that they mimic design. If artificial, it would merely confirm what many already suspect, that intelligence is not unique to Earth, but a universal phenomenon, woven into the fabric of cosmic evolution. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.